Dear colleagues, good morning, good afternoon, good evening, good night. We start our seminar, and today we have the pleasure to have our speaker, Professor Alexandr Zubkov. He is now in United Arab Emirates University, and he will speak on Harish-Chandra pairs and group superschemes. Please, you can start, Alexandr.
Thank you very much, Paolo. So let me show my first slide. But let me start with my thanks to Ivan Pavlovich, who invited me to give this talk. And this is my pleasure to share some recent results obtained with my co-author, A.Masuoka from Tsukuba University, Japan. With you, I mean, with so nice and great mathematicians. Okay, so let me just proceed to the second slide, because okay. So let me just remind you some elementary, some preliminary notations which I'm going to use in this talk. So let me just remind you what kind of objects will be involved in my talk, and let me start with the notion of superspace. First of all, throughout this talk, a superring means just zeta2 graded ring with homogeneous components R0 and R1, right? And the elements from the component R0 are called even elements, and the elements from the component R1 are called odd elements. And also we can define something like a parity of element. So if element belongs to component R0, its parity is 0. So this index is just exactly the parity of the element from this component. And 1 is the parity of any element from this component R1. And in what follows, I'm going to use only so-called supercommutative superrings. What does it mean that they are supercommutative? It means that for any couple of homogeneous elements, say A and B, these elements satisfy this anti-commutativity identity, like A times B is equal to minus B times A, provided that A and B belongs to the component, belongs to the odd component of this superring. Otherwise, these elements just commute to each other. Okay. Also, in what follows, I assume that this superring doesn't have any two torsion. So I mean that 2 is an invertible element. It's easy to see that any prime or maximal superideal of R has the following simple form. So the even component of this superideal is a just prime or respectively maximal ideal of the even component of our superring. And the odd component just coincide with the odd component of whole ring. Okay. And next, a superspace X is a just pair consisting of topological space, which will be denoted by this symbol X in brackets. Okay, and this O sub X is a just sheaf of supercommutative superrings defined on this topological space. And also I assume that for any point X from our underlying topological space, the Stock superring, this O sub X, is local superring. So it means that this, as in a pure, I mean that in the pure even case, this superring contains the unique maximal superideal. Okay. Oops. So superspaces, it's clear that superspaces form a category with whose morphisms are just couples of two morphisms. So first morphism is a morphism of the underlying topological spaces, right? So this morphism is just a homogeneous morphism of these topological spaces. And the next morphism is a morphism of sheaves of superrings. So here, O sub y is just sheaf on the superspace Y, capital Y. And this is a pullback of the superring sheaf of the scheme of superspace X. Okay, satisfying some natural conditions. And also we assume that for any point X from the topological space of superspace X, and for any such point, the induced superring morphism of local of stocks, of the corresponding stocks, is a just local morphism. It means that this induced superring morphism just takes the maximal superideal of this local superring to the maximal superideal of this local superring. Okay, it's a standard definition, which is just some superization of the definition of scheme or space, geometrical space. And now let's define the superschemes. First of all, let's consider some superring A. Let me remind you that all superrings are supposed to be supercommutative. And on a set, on a prime spectrum of this superring, regarded as a topological space with the standard Zariski topology, one can define a sheaf of superrings in the following way. So it is just for any open subset in this Zariski topological space, we can consider all locally constant functions from this subset to this collection of local superrings, right? So for each prime ideal, let me remind you that the points of this set U, points of this set U are exactly the prime superideals. Okay, for each such a superideal, we can define the corresponding local superring, and this function is defined to be from this open subset to this collection of local superrings, such that for any point P, f of P belongs to the corresponding localization. And the resulting superspace is called affine superscheme, and it is denoted by this symbol. It's a double aspect of A. Of course, this is a definition which was created by Dmitry Leitis many years ago in the 70s. But you see that somebody who is familiar with algebraic geometry can immediately realize that this definition is quite close to the standard definition of affine scheme by the Grothendieck. So it's just superization, very natural superization of Grothendieck's ideas. So Grothendieck's definition of a scheme. And next, a superspace X is called a superscheme whenever there is a covering of underlying topological space by open subsets U sub I, such that for any index I, the open superspace, what is it? We have to restrict the original sheaf of super rings to our open subset, right? Of course, we will get some superspace, right? Defined on this open subset, U sub I. And this superspace should be isomorphic to a fine superscheme, right? Corresponding to some superring, A sub I. Okay, so it's clear that superschemes form a full subcategory in the category of superspaces. And with each superscheme X, we can associate a scheme X sub if such that the underlying topological space of this scheme is exactly the underlying topological space of X. And the structural sheaf of rings now is defined as follows. We have to consider the sheaf of superideals generated by odd elements of this sheaf OX, right? And we have to consider this factor sheaf. In general, it's not a sheaf. It's what is called in algebraic geometry like a pre-sheaf. But the sheafification of this pre-sheaf defines a structural sheaf of rings, right? Because I just killed all odd elements. So now this is a sheaf of rings, not of super rings. So this scheme, it's easy to see that it's exactly scheme in the sense of Grothendieck. This scheme can be regarded as the largest closed, purely even super-subscheme of X, right? By the trivial reason, because you can regard any scheme as some superscheme with trivial odd structure. Okay, and also let me note that the full subcategory of affine superschemes is just anti-equivalent to the category of supercommutative super rings with graded morphism. Okay. Next. Next. Okay, so assume that we have some superscheme X, and I say that this superscheme is locally algebraic if there is some affine covering of X by open affine super-subschemes, right? Open affine super-subschemes of this form, with each superring AI to be a finitely generated K superalgebra, where K is a field of zero or odd characteristic. Okay, so there is no necessary that I'm not assuming that this covering is finite. So it's covered by possibly infinitely many open affine super subschemes. But in the case when we have finite covering, I will say that this superscheme is just algebraic superscheme, not locally algebraic, but just algebraic. Okay, and now, so everything is prepared to define supergroups in our category of locally algebraic superschemes. So any group object in the category of locally algebraic superschemes is called an algebraic group superscheme. So what does it mean? It can be defined in a categorical terms, in terms of diagrams, right? It means that our superscheme, denoted by G, has some morphisms, like first morphism from the square of G to G, which is nothing else but the multiplication morphism, right? Next morphism from G to G, it is just inversion morphism. And also we have this morphism from the one-point superscheme, a double aspect of the field K. So underlying space of this superscheme is just 1 point. And this 1 point is identified with the identity element of this group object. Okay, and this morphism should satisfy some standard properties of a group, like this multiplication should be associative, and you know that we can define the associativity of M in terms of diagrams, right? And also some properties of inversion, morphism, and so on. I think it's more or less clear for anybody. Okay. And for the sake of shortness, I will call any locally algebraic group a locally algebraic group superscheme by, I will call it just a supergroup. Okay. Now there is another equivalent language for superschemes and for supergroups. This is so-called functor of points language, I mean the following. So assume that we have a category of supercommutative K superalgebras, right? Okay, and we have also the category of sets. And with any superscheme X, one can associate the functor of points from the category of K superalgebras to the category of sets. And it is defined in the following way. This functor X of R, where R is some superalgebra, it is nothing else but the set of all morphisms of these superschemes. So the first argument is just a fine superscheme defined by this superalgebra R. Next argument is our superscheme X. It's easy to see that it's some functor, right? Depending on this R. Okay. And by Yoneda lemma, which is pretty standard statement in a category theory, by Yoneda lemma, the functor which associate with the superscheme, this functor of points, is some equivalence between the category of superschemes and some certain full subcategory of the category of functors from superalgebras to sets. These are exactly some, how to say it. I'm not going to so deeply to all this terminology, but well, I can say that these functors of points, they should be so-called local functors, and also they should be covered by affine functors of points. So more or less the same as a definition of superscheme in Grothendieck sense. Okay, for example, some trivial example. A fine superscheme, double S spec of A, is associated with the following functor. So this, which is denoted by the symbols, double SP of A of R. It's nothing else but the set of all superalgebra morphism from R to R, right? Okay. And also we can consider our supergroups as functors of points. And it's easy to see that if G is a superscheme, is a group superscheme, G is a, okay, it's better to say supergroup, right? So it's easy to see that G is a supergroup if and only if the corresponding group functor, functor of points is a group functor. In other words, it is a functor from the category of superalgebras to the category of groups. And let me give you some illustrating example of such supergroup. It is a well-known supergroup called a general linear supergroup. So this is general linear supergroup GL of M. M, regarded as a group functor, is defined as follows. So for any superalgebra R, the group GL of R consists of all invertible matrices of this block form, block matrices, with two even blocks, A and D. So these A and D are matrices with entries from R0, right? So the entries of this block are 0 elements. And block A has size m times n, block D has size n times n, block B and C, their entries are exactly the elements of the odd component of our superalgebra. So B and C are odd blocks of the sizes m times n and n times m respectively. Right, so the size of this matrix is m plus, the order of this matrix is m plus n. Okay, and okay, so this matrix is invertible if and only if these even blocks are invertible matrices. So it means that determinants of A and D are invertible elements in the component R0. This is the definition of general linear supergroup. Let me note that general linear supergroup is a affine supergroup. So as a superscheme, it is a affine superscheme defined by some superalgebra of coordinate functions, right, on this superscheme. Okay. Okay, let me also define the following. That diagram in the category of supergroups, like this, is a short exact sequence in the category of supergroups. If and only if the corresponding diagram of group functors is a short exact sequence in the category of certain sheaves. What does it mean? It means the following. So for any superalgebra R, if you will consider the groups of points like H of R, G of R, L of R, right? You know that since these are group functors, they are functors to the category of groups. So these sets of R points, they are exactly some abstract groups. So H of R, G of R, and L of R, they are just groups. And the exactness of this sequence means that this sequence is left exact. And also, what does it mean, the right exactness of this sequence? It means that the following: it's not the exactness as abstract groups. It's something different. So there is no necessary that the image of G of R in L of R. I mean that the image of G of R coincides with L of R. It is not necessary. But for any element G from L of R, there is a so-called FPPF covering of R prime of R, such that the group homomorphism from L of R to L of R prime takes this element to some element from the image of G of R prime in L of R prime. So up to this replacing of this R by some FPPF covering R prime, we can say that this morphism is surjective, right? Up to some change of this R to the FPPF covering. And what this FPPF covering means? It's a definition which is due to Grothendieck again. It means the following. It means that this superalgebra R prime is, first of all, finitely presented R superalgebra. So there is a morphism from R to R prime, with respect to which R prime is finitely presented R superalgebra over R. And also R prime is faithfully flat R supermodel in the standard sense of commutative ring theory. Okay. Okay, so one can define, as in a pure even case, we can define Lie superalgebra of any supergroup in a more or less standard way. You know that there is some standard definition with the help of so-called dual numbers. Okay, also introduced by Grothendieck. And what is it? So for any superalgebra R, we can define this superalgebra of dual numbers, right? R of epsilon 0, epsilon 1. So epsilon 0 is an even element, epsilon 1 is an odd element, and any product of these two generators is equal to 0. In particular, for example, epsilon 0 square is 0. Epsilon 1 square, okay, should be 0 because it is odd element. And any product epsilon 0 times epsilon 1, it is also 0. So we have a superalgebra morphism from this superalgebra of dual numbers to R. It's a sort of augmentation map, right? So these components, depending on epsilon0 and epsilon1, should be taken to 0. Let me denote this morphism by this iota sub R. And the Lie superalgebra can be defined in a standard way as the kernel of the induced morphism. So Lie of G of R, because Lie superalgebra is just functor, depending on the ring of superalgebra of coefficients. And this is nothing else but this kernel, because we have this group homomorphism from G of superalgebra of dual numbers to G of R. And this morphism is induced by this superalgebra morphism, iota R. And Lie superalgebra is just the kernel of this group homomorphism. Okay. And really, this functor can be defined by its set of k points over field k. So one can show that Lie of G of R is just Lie of G of k tensored by R. And it is just Lie R superalgebra. And Lie bracket is uniquely defined by the Lie bracket of K superalgebra, Lie of G of K. As in the case of locally algebraic group schemes, one can define the conjugation action of G on itself, and we can define induced adjoint action of G on its Lie superalgebra, right? It's a just differential of conjugation action of G on itself. Okay, now, so everything is prepared to define category of Harish-Chandra pairs. So I assume that G is a local algebraic group, and the Lie algebra of this local algebraic group, it's not supergroup, it's just group, is denoted by this lowercase g. Okay. This pair, and we have some pair G comma V, and this pair is called a Harish-Chandra pair if and only if the following hold. First condition, this sum G plus V has a Lie superalgebra structure with even and odd components G and V respectively. So this first summand is an even component and V is an odd component of my Lie superalgebra. And next, more important property. Lie super bracket, I mean that the Lie operation on this Lie superalgebra induces the symmetric bilinear G equivariant map from V times V to G. What does it mean? We know that V is a G supermodel. Oh, sorry, G model, right? So therefore, we have diagonal action of G on this product, V times V, right? And this action commutes with the action on G, with the adjoint action, with respect to the adjoint action of G on its Lie algebra. Okay? So if two conditions are satisfied, we call that this couple, I mean this pair G comma V is a Harish-Chandra pair. And let me, okay, so, okay, of course, this, how to say it, collection of Harish-Chandra pairs form some category. So Harish-Chandra pairs form a category with morphisms to be some couples of morphisms, like a phi f here. So it seems that I have two Harish-Chandra pairs, G comma V and H comma W. Then a morphism from this pair to this pair is a just couple of morphism, phi and f, where phi is a morphism of local algebraic groups, and f is a morphism of vector spaces. such that the following diagrams are commutative. So here we have this. Okay, so you see that this arrow is just this Lie bracket, right, on V to the even component. And here also we have this Lie bracket on this product, V times W times W, right? With the image in the corresponding Lie algebra. Here, the vertical arrow is just F times F, right? Here, this differential of phi. So this diagram is commutative, okay? And also, this diagram is commutative. It means that the action of G on V, right, commutes up to this morphism phi. Oh, I mean something different. I mean that if for example, if you consider some element from this locally algebraic group, then we have this action of this element on some element of this space, right? Something like a G, okay, something like a G times V. Then the map F takes this G times V to phi of G, which is element of H, times F of V, right? This is why, I mean, this is the meaning of the commutativity of this diagram. Okay? And the most important example of Harish-Chandra pair is as follows. Assume that we have a supergroup G, and we can associate a natural Harish-Chandra pair as follows. So the first component is just largest purely even super subgroup of G, this G sub if. And you know that we can regard this purely even supergroup as just some group, by which I mean group scheme. So it's just group scheme. Purely even supergroup means that just group scheme. And the second component is just odd component of Lie superalgebra of supergroup G, right? And the action of this G if on G1 is just induced by the adjoint action of G on its Lie superalgebra G, right? Because it's clear that the action of even component just preserves the parities of elements in Lie superalgebra G. So this subgroup G if takes G0 to G0, right? And G1 to G1. Okay. Well, and this bilinear map is nothing else but Lie bracket on this Lie superalgebra. And we have some functor from the category of supergroups to the category of Harish-Chandra pairs. This is a covariant functor, right? And I will denote this functor by this symbol, HC, and I will call this functor Harish-Chandra functor. And now we can formulate the main theorem in our joint work with Masuoka. So this functor is just equivalence of categories. So the category of locally algebraic group superschemes is equivalent to the category, to a certain category of Harish-Chandra pairs. Let me just give you some, maybe few details about it using my tablet. Well, the problem is to construct some supergroup for a given Harish-Chandra pair, right? So assume that we have some Harish-Chandra pair. So here G is a just group scheme, V is a just G model. So how can I construct the corresponding supergroup? So we can prove that the corresponding, how to denote it? Okay, let me use this symbol. We can construct this supergroup G in the following way. So it is as a superscheme. What's going on here? As a so I don't know what's going on. Well, let me try again. Oops, it's working. As a superscheme is just a direct product. Okay, and here. So what I mean by this? So here there's a first component is just a purely even superscheme, right? Which is nothing else but this group scheme G. And this is just a affine superscheme defined by this superalgebra. And lambda of V is a Grossman algebra. Grossman algebra regarded like a superalgebra. If we will define the parity in such a way that all elements of V, so elements of V are odd. And next, of course, it's not a product of some subgroups. It's not a product of subgroups. So the structure of this supergroup is not so trivial. But how can I define the structure, the group structure on this direct product? I have to define the action of G on this, how to say, purely odd superscheme. And this action is defined by action of this G on the space V. And also we need, for example, we have to define the product of elements of this component, right? And these products, if you will consider two elements, say G1, G2, from this component, then the product of G1, G2 has the following form. It can be defined exactly as some element from first component. Okay, let me define it by F. It depends on G1, G2 times some element from this component. Let me denote it by H. And the main problem is how to define this element F and this element H. Okay. So here, okay, I just wrote some piece of history. Right? So first phrase, I have already mentioned that. That for the first phrase, I have already mentioned that the notion of superscheme was introduced by Dmitry Leitis in 1974. The method of Harish-Chandra pairs is not absolutely new, and the first application of this method was due Koshul in 1982. Later, this method was extended for analytic and affine supergroups over fields of zero characteristic by Carmeli Fiordesi and Elizaveta Vishnyakova in 2011 and 2013, and over a field of arbitrary characteristic, and even more generally over a certain commutative ring without two torsion. This method of Harish-Chandra pairs was developed by A.Masuoka and his PhD student Taiki Shibata. And the above theorem is just further generalization of this method for all, not necessarily affine supergroups. And since we are working in a much more wider category of superschemes, of course, we were supposed to develop some extra technique, like a technique of formal supergroups, hyperalgebras, sorry, in order to construct this quasi-inverse of Harish-Chandra function. Okay. And now I'm going to say something about applications of the main theorem. And the first application is the so-called Barsotti-Chevalley, superization of Barsotti-Chevalley theorem. So let me remind you that it is a well-known theorem in the theory of algebraic group schemes, which says that some connected algebraic group scheme is just extension of normal affine subscheme, group subscheme, by some abelian variety. So up to this abelian factor, any group scheme is just affine group scheme. And in a category of supergroups, we have more or less the same phenomena. So if G is a connected algebraic supergroup, then this G contains connected normal super subgroups, say N1 and N2, such that the first super subgroup N1 is affine. In other words, this super subgroup N1 can be represented by matrices. So it is just subgroup of some general linear supergroup for sufficiently large parameters M and N. And next extension, so the factor N2 over N1 is a just abelian purely even group variety. So nothing new here, right? So this factor is just abelian purely even group variety. And the next factor is again some affine supergroup, not necessarily purely even, but some matrix supergroup. Okay, so we have more or less, I would say, analog of Barsotti-Chevalley theorem. And okay, in this direction, we can define, as in a category of group schemes, we can define so-called pseudo-abelian supergroups. So let me remind you that algebraic supergroup G is called pseudo-abelian if G does not contain non-trivial connected affine super subgroups. There is no there are no super subgroups like this N1 in this theory in G. In the category of group schemes, it means that your group is just abelian variety. So by the classical Barsotti-Chevalley theorem, any pseudo-abelian group is just abelian group variety. For example, it can be, so the typical example of abelian group variety is any elliptic curve. And also we have to assume here that ground field is a perfect, but as some sort of mild condition. But what's interesting here is that in the category of algebraic supergroups, it's not longer true. So we have the following proposition, which gave us a lot of counterexamples, right? So the proposition, again, has been proven in our joint work. So the following hold. First of all, if G is a pseudo-abelian supergroup, then its even component is a product of abelian variety and some affine normal subgroup R. So this is a necessary condition. But what's interesting, we have a sort of converse of this statement as follows. So conversely, if some algebraic group H is a product of some abelian group variety N and a affine normal subgroup R, then there are infinitely many pairwise non-isomorphic pseudo-abelian supergroups G, whose even part is isomorphic to this group H. So we can construct infinitely many some pseudo-abelian supergroups which are not abelian varieties. Because of any abelian supergroup is uniquely defined by the condition that its even part is abelian group variety. So any abelian supergroup is defined by this property. Its even part is just abelian variety. But here you see that this subgroup R can be non-trivial. So therefore H is not abelian variety in general. But nevertheless, you can construct some supergroups with the even part H, which are pseudo-abelian. But H, even part of G, is not abelian variety. And therefore G is not abelian variety also. I mean that not abelian supergroup of variety. Okay, so next application is about this fundamental theorem. I mean the superization of this fundamental theorem in the theory of algebraic groups, which states that for any algebraic group G and for any subgroup H, the sheaf quotient. Sheaf quotient means that quotient which is a completion of some naive quotient in the Grothendieck topology of FPPF coverings. And let me denote this sheaf quotient by this standard symbol G over H. And the statement of the theorem is as follows. This sheaf quotient is always a scheme of finite type if G is algebraic group. So this is a well-known theorem. It has been proven in this well-known book. Probably anybody knows this abbreviation, SGA. This, how to pronounce it in French, seminar of geometry, seminar de geometry de algebraic. Oh, okay, I give up. I don't know how to pronounce it in French. Okay, so this is a well-known seminar by Grothendieck. So in the 5th chapter of this book, you can find the proof of this theory. So what we did? We did the following, so we obtained the following results. Assume that G is an algebraic supergroup, and H, it's not necessarily normal, super subgroup. We proved that the sheaf quotient G over H is again a superscheme of finite type, right? But for the first time, we have proven this theorem in the case when G is a affine supergroup. This our article had been published in Journal of Algebra, roughly about 10 years ago, maybe. And now we just generalize this theorem for arbitrary groups, for arbitrary algebraic group superschemes. So this sheaf quotient, G over H, is a superscheme of finite type for any G, for any algebraic group superscheme G, and for any its super-subscheme, group super-subscheme H. So now we have this theorem in a full generality. Okay. Well, I don't know, probably, I estimate so my time, left time, like 10 minutes, right? Okay. Let me just...
Yes, okay.
let me finish with some actual problems, for which I'm sure that their solution will bring some significant progress in this theory of group superschemes. As in purely even case, we say that a fine algebraic supergroup G is a reductive supergroup if G doesn't contain any non-trivial normal connect unipotent super subgroups. Unipotent means more or less the same as in a purely even case. So since our group is algebraic and affine, I can embed this supergroup G to the group of matrices. So G is just a super subgroup of the group of the general linear supergroup. So G can be regarded as a supergroup of matrices. Okay, and a fine supergroup is called unipotent if and only if, with respect to the change of base of underlying vector superspace, this supergroup is a subgroup of upper triangular supermatrices in a standard sense of this word. So it's just super subgroup of the supergroup of upper triangular supermatrices. Okay. It is long known that over good field, say algebraically closed field, any reductive group is almost isomorphic to a direct product of simple algebraic groups. Almost isomorphic means that our group is just this direct product over some finite subgroup, so modulo some finite subgroup. But in the category of supergroups, this situation is completely different. And let me just note that using this Harish-Chandra pairs method, one can construct some reductive supergroup G such that its even component is a trigonalizable group. Right? In the category of algebraic groups, it's just nonsense, because the group of triangular matrices cannot be reductive. It always contains some huge unipotent radical, except the case when this group is just the diagonal group, the subgroup of maximal torus, up to some conjugation, of course. So in the category of group, it's not possible. It's a complete nonsense. But here, it's possible that the even component is just a supergroup of triangle matrices, right? And even we can say even more. If, for example, this even component is smooth group, so it is, I mean that as a scheme, it doesn't have any singular points. Or you can say that the connected component of this group, no, sorry, I'm wrong. It cannot be defined in terms of connected component. Okay, it doesn't matter. So if this even component is a smooth group scheme, then in this case, G will be solvable, a reductive supergroup. It's pretty strange. Right, so we can construct the solvable reductive supergroup. So it means that in the category of supergroups, this property to be reductive, it's quite far from the same property for group schemes. So there are many strange reductive supergroups, and it raises the problem one, right? So describe reductive supergroups in terms of maybe some filtrations by normal super subgroups with exactly specified factors. Let me just explain what I mean by this. I mean the following. I expect that, of course, okay, we know that there are many strange reductive supergroups. but maybe any reductive supergroup has some filtration by normal super subgroups, whose factors, maybe some of these factors are solvable reductive supergroups of some specific type, which should be described also. And another factors, maybe just purely even reductive algebraic groups, something like this. Or maybe there are many other specific factors. I don't know right now. So this problem waits somebody who will investigate the subcategory of reductive supergroups completely. But what I can say, it's a very difficult problem. And next problem is also a very natural problem. We know that there is some Katz classification of simple Lie superalgebras, right? And also we know that there is a classification of simple Lie groups. And these simple Lie groups or simple Lie superalgebras, more or less, they correspond to some Dynkin diagrams, right? So they can be at least over algebraically closed field. So each simple Lie algebra corresponds to some simple algebraic group, right? And vice versa. And also we can construct some algebraic supergroups which corresponds to simple Lie superalgebras in Katz classification. But now the question is, we can define, for example, okay, how to formulate it? It was a work by Fiore with co-authors, in which they construct some Chevalley supergroups corresponding to the almost all simple Lie superalgebras over arbitrary field of arbitrary characteristics. This work was also extended by A.Masuoka and one of his PhD students in terms of these Harish-Chandra pairs. But so far I know, some of simple Lie superalgebras, for some of simple Lie superalgebras, so far we don't know some corresponding construction, a typical construction like a construction of the corresponding Lie supergroup. Not Lie exactly, but algebraic supergroup in terms of a sort of, I would say, Chevalley supergroup, in terms of some Chevalley supergroup construction. But also, I mean that this question seems to be quite natural because we know how to construct any supergroup. We know what we need is just to have this couple, like even, purely even, or just group scheme, algebraic group scheme, or just algebraic supergroup, right? And we know that, for example, we assume that the corresponding Lie superalgebra is just one of these simple Lie superalgebras. So therefore, what is the problem here? We have to define the action of even part on this Lie superalgebra somehow. And using this action, we can construct the corresponding algebraic supergroup, right? So now the question is it always so that in any way, I mean that for any action of this even component on Lie superalgebra, we will get one of the well-known simple algebraic supergroups. Okay, hope that I explain this problem. I'm not sure about it, but I hope that, well, I did my best. Okay, so I think that my time is over. So Ivan Pavlovich, so I'm done.
Okay. Now, questions, comments, please. There are some things in chat.
In chat.
In chat, there are just thanks, not questions. I don't see questions, but thanks.
Yes, thank you very much.
Many thanks. Okay, and questions and more thanks. More thanks. Okay, while people, you can think about, prepare more maybe questions, I just want to make announcements. You are thinking about, you may think more about questions or comments. The next Thursday, we will have a talk by Maria Gorelik from Technion, Israel, and she will speak on depths and cores in the light of DS functors. The next Thursday, Maria Gorelik. So see you again the next Thursday. And still, some questions or comments to the talk of Alexandr? Okay, I want to congratulate Alexandr for very impressive results, very impressive results, and thank you very much for your talk.
Thank you very much.
Let's thank. Okay, the announcement was done for the next Thursday, so see everybody the next Thursday. Thank you for everybody for coming for participation. Bye-bye.
Bye.